Right, good afternoon, everyone. I'm hoping that you can both see and hear me, and I'm hoping maybe someone can just pop into the chat and just put a thumbs up or a yes or something, just so I know that we're all connected properly. So thumbs up or a would be great. Otherwise, I'm not sure that I'm connected, but I'm going to trust that I am. Right. So we're going to dive straight in, and today is probability and counting techniques. Such a nice topic if you understand it. Really, really straightforward. And so let's, without any further ado, dive in. Welcome to all of you. And just a quick reminder about kind of how these live streams work. The questions that we're going to answer each day are available on simi.education. And ideally, you want to try them before you watch the video. That's how you'll get maximum benefit. Otherwise, you can watch them obviously. So you can try them while we do the video, but much better to try them beforehand. And then at the end of the live session each day, you can download the solutions to the questions off the website as well. If you are finding this useful, please like, share, subscribe, right? Tell your friends, and let's see if we can get thousands of people watching these videos. Okay, wonderful. So that's basically all by way of introduction. What we're going to talk about today are kind of what formulae are we given, what are we not given, right? So in terms of the probability, we just given those two formulae that are in blue. And in fact, the first one is really not all that useful. It says that the probability of something happening is the number of ways it can happen divided by the total number of things that can happen, the number of things in the sample space. And it's a fairly obvious formula. The next formula is a very, very useful formula, and it tells us the probability of A or B. And basically, that's the sum of the probabilities of A and B minus the probability of A and B. Right. The things that we're not given, that if I was going to write the exam that you're going to write, the things that we're not given that I would kind of make sure I knew is the idea of a complement. I've written it in two different ways. So E with a line on top or E with a little dash is means not E. All right. So the probability of E plus the probability of not E is 1. That also makes complete sense. Probability of it raining, 30%. Probability of it not raining, 70%. Okay, really, really important idea is that the complement of at least 1 is none. Right, so the balance of the probabilities of at least 1 is the probability of none. And we'll look at that as we do some examples. Then there are two really big ideas. One is that if things are independent, it means they don't influence the outcome of one another. So for example, tossing a coin and tossing it again. Those are independent things. What happens on the first toss of the coin? No bearing on what happens on the second toss. Or tossing a coin and tossing a die. Totally independent of one another. Now, if things are independent, then the probability that they both happen, A and B, is the product of their separate probabilities. And the other way around. If the product of the separate probabilities is the same as the probability that they both happen, then they are independent. So in other words, the one thing happens, the other thing has to happen. A little bit like alternate angles, lines parallel, alternate angles equal. But also, if alternate angles are equal, then lines are parallel. So you can't have the one without the other. If A and B are independent, then the probability of A and B is the product of the probabilities. And the other way around, you'll see that arrow has got a kind of a double head on it. It goes both ways. If the probability of A and B is equal to the probability of A times the probability of B, then A and B are independent. Okay, the next and last concept in the probability is the idea of things being mutually exclusive. Mutually exclusive means that they cannot both happen. And if things are mutually exclusive, if A and B are mutually exclusive, then the probability that they both happen is 0. All right, they cannot both happen. Okay, an example would be being in, for a learner in your school to be in grade 8 and in grade 9. Okay, probability of that is 0. All right, an example of a non-mutually exclusive thing would be a student in your school being in grade 12 and being a girl. All right, both those things can happen. Okay, right. So that is you'll see there are no formulae given for counting techniques. I want to just sort of talk a little bit about those, right? And I'm going to talk about something now called the fundamental counting principle. Okay, and basically what I've got here is I've got a couple of pairs of sunglasses, some like really cool sunglasses, and then I've also got so I've got two pairs of sunglasses, and I've actually got three different caps as well. All right, I've got a red one, I've got this rather nice Elliot May one, and then I've got my my fishing cap, right, my fishing hat. Okay, so the question I have for you is, if I've got three caps, right, which I've shown you, and two different pairs of sunglasses, then how many outfits can I make? And the answer is actually going to be six, right? And the reason it's going to be six is with this cap, so let's count them. With this cap, I can have these sunglasses, that's one. I can have these sunglasses, that's two. Now I can change caps, all right, and I can have now three, that cap with these sunglasses, that cap with these sunglasses, that's four. And then lastly, my Ilian May cap, all right, which is actually my favorite. I don't know which one you guys like the most, but five and six. Okay, and that six came about from 3 times 2. Three caps and two pairs of sunglasses. All right. If I then also had maybe, I don't know, two different types of earrings that I could wear, then it would double up again because it would be 3 times 2 times 2. Because with any combination of cap and glasses, I could choose either either of the um, either of the earrings. Okay, right. Onwards and upwards. So that's this idea of the fundamental counting principle. Just multiply things. Right. The next thing is the whole idea of just arranging some things in an order. All right. And so what we've got here, we've got 4 blocks: a red, a blue, a green, and a yellow. And we're going to arrange them. Now, for the first position, there's a choice of 4 different colors. We could either have the red one first, or the blue, or the green, or the yellow. Now, for the next position, we got a choice of 3. So if we went with the red, you'll see we could have gone red, blue, red, green, or red, yellow. But equally, if we'd gone with the blue, we would have had a choice of 3. So we had a choice of 4 for the first block, a choice of 3 for the second block. Now, if you look, we've got red, blue, I'm just looking at the top left there. We got red, blue, green, and yellow. So now I've got a choice of either blue or green in the top left row. Okay, so I've got a choice of 2, and if I put those choices of 2 in, you'll see I've now got the red, blue, yellow, and I've also got the red, blue, green. So it doubled up. All right, you'll see it doubled up because it went from 4 times 3 times 2, and in fact for the last block now I actually don't have any choices, because in the top left, I've got to now put in a green block, and if we go down to the bottom right, I've actually got to put in a blue block. All right, so when I there it is, it's going to be 4 times 3 times 2 times 1. So if we've got 4 different objects, then we can arrange them in 4 factorial ways. That 4 with an exclamation mark is not 4, all right, it's 4 times 3 times 2 times 1. Okay, so I'm just going to go back on this slide and just show you that again. All right, so choice of 4 for the first block. And then with any of those 4, we could choose 3 choices for the second block, because we've already used one of them for the first one. And so it's 4 times 3. And then now we've got a choice of 2 for the next one. So it's 4 times 3 times 2. And then actually no choice for the last block. It's, well, one choice. One is not really a choice. A choice is when you've got 2, right? Just one that we can put in there. All right. So there it is. The 24 ways we can arrange 4 objects. If we've got n objects, it'll be n factorial. Okay, so that's that idea. The next thing is sometimes we want to keep objects that are together. Right. So here there are 6 different blocks, okay, and 3 of them have got dots on for whatever reason. I want to know how many ways can I group these things, but I want the ones with dots to stay together. This could be a group of friends going to a movie. It could be books by a certain author on a shelf. It could be your shirts hanging in a cupboard and you want the green ones together. What's important here is that these ones that we want to keep together, they are different to one another. They've got some reason, some shared property that we want to keep them together, but they are actually different. You can see them there. They're yellow, green, and orange. Right, now the little conceptual trick here is that we put a rubber band around those that we want to keep together. All right, so there they are. Now, we've actually now only got 4 objects. We've got the composite object, the big one, and we got the red one and the purple one and the blue one. So we've got 4 objects. How many ways can we arrange 4 objects? Yeah, I hear you say it. 4 factorial. All right, so let's have a look. Okay, 24 ways. But for any one of those 24 ways, those 3 that are in the rubber band, all right, can be arranged themselves. They can mix around in there in 3 factorial ways. So in fact, what we need to do is we need to take our 4 objects and then we need to multiply by 3 for the fact that the 3 inside can switch around. Okay, I'm just going to tell you the 6 orders that those 3 inside can go in. Yellow, green, orange, yellow, orange, green, green, orange, yellow, green, yellow, orange, and then orange, yellow, green, and orange, green, yellow, 3 factorial. Okay, all right. So that's a really important idea, keeping some things together. And then lastly, before we dive into our examples, what if some of the things are identical? Okay, so I think I'm on the wrong slide here, so I'm just going to, there we go. All right, suppose we had these 6 blocks. Now at the moment, I've put tiny little marks on 2 of the green ones so that the 3 green ones actually appear to be different. All right, and if they were different, then obviously there would be 6 factorial ways we could arrange them. But in fact, those green ones are not different. Okay, so if we look, there are actually 6 ways that we can arrange those. If we were counting them differently, you'll notice there's one with a dot, a blank one, and one with a cross. And you'll see that I've got all 6 different ways. Those are actually the same because those green blocks are actually the same. Right? It's almost like they've got a tiny little mark on, which you could see really close, or with the magnifying glass. When you take the magnifying glass away, they look identical. So we're actually counting, if we go 6 factorial, all right, just to go back here, if we go 6 factorial, we're actually counting these ones as different, but they're actually all the same. So our answer needs to be divided by 3 factorial. It's 3 factorial times 2 big. So in fact, the answer is going to be 6 factorial divided by 3 factorial. Little rule here, total number factorial, and then you divide by factorial for the number that are repeated. And if there are 2 different things repeated, so suppose there were now 2 red blocks added here, all right, then it would be 8 factorial, because there's a total of 8 blocks, divided by 3 factorial, because 3 of them are green and identical, and then also a 2 factorial on the denominator as well for the 2 red ones, which are identical. Okay. Hopefully this will all make a lot of sense to you as we kind of go through, and we can just get the right screen up. Then all right, there we go. So we're going to dive straight into some probability, and here it is. So first up, a die is thrown and a card is drawn from a pack. Determine the following probabilities. What's the probability of a 3 on the die and a red card? I've used the symbol for and. I think in your exams, they might use the word, they might use the symbol, they might use both. Right. These things are independent. What happens on the die and what happens with the card are completely independent of one another. Do not influence one another. So in fact, this will be the probability of a 3 times by the probability of a red. Right, the probability of a 3 on the die, and this is where this formula, which as I say, this is really completely obvious. What's the probability of a 3 when you throw a die? Well, how many ways can you get a 3? 1, all right, out of 6. What's the probability of a red card? Well, half the cards in the pack are red, all right, so there it is, and we get an answer of a 12. Okay, next up. What's the probability of a prime number on the die and a heart? Again, because these things are independent, we can just multiply. So it's going to be probability of a prime multiplied by the probability of a height. Right, and the probability of a prime, well, how many prime numbers? Remember, 1 is not prime. 2, 2, 3, and 5. So in fact, it's actually 3 of the 6. That's, again, we're using this formula here. There are 3 ways we can get a prime number out of a total of 6 things. And the probability of a height, well, there are 4 suits in the pack, and a quarter of them are heights. So this is going to be 3 6 times a quarter, 3 6 times a quarter, 3/24, 1/8. Okay, right. Now, this is OR, and this is the formula that we get provided. The probability of a factor of 9, right, or a black card will be the probability of a factor of 9 plus the probability of a black card minus the probability of a factor of 9 and a black card. Now, you can't necessarily multiply those unless you know that these things are independent, which they are. So the probability of a factor of 9, well, the factors of 9, the only factors of 9 on a die are 1 and 3. So that's actually going to be 2 out of 6. This is going to be half the cards are black. And then because these things are independent, the probability of both of them happening is just the product of them, of the 2 probabilities. So this is in fact going to be 2 out of 12. Right. And so what we end up with is 2/3, in fact. All right. Probability of an even on the die or a spade, exactly the same idea. They are independent, so we could say probability of even plus the probability of a spade minus the probability of an even and a spade. Right, so the probability of an even, easy, 2, 4, 6, 3 out of 6. The probability of a spade is 1 out of 4. And the probability of both will be the product. So it'll be 3 6 times a quarter because they are independent things. Right. Slot all of that into a calculator and we get 3/8. Okay. Right. Onwards and upwards to question 2. And it says, 2 friends are comparing their chances of getting a ticket to a certain concert. Suppose Tandi has a 40% chance, Bongi has a 16% chance, and there's a 6.4% chance that both get a ticket. Are these things mutually exclusive? No. Right. Okay, because the probability of Bongi or Tandi and Bongi is not 0. Remember, when things are mutually exclusive, the probability that both happen is 0. Here it's not 0. There it is over there. It's actually 6.4%. Now, are they independent, right? And this is just an important thing here. We're not going to put probability of Bongi and Tandi. I'll tell you what we're not going to do. We're not going to do this. Equal to probability of Bongi and Tandi. We don't know if they're equal at this stage, right? So we're going to work, it's very much like, almost like an identity. Don't put them equal. We're going to check if they are equal. Right, so it's like a left-hand side, right-hand side thing. This we know. This is 6.4%, okay, or 0.064 if we want as a decimal. If we take the probability of Bongi, 0.4, and we multiply, sorry, that's not the probability of Bongi. Probability of Bongi is the probability of Bongi is 0.16, 16%, times 0.4. When we multiply these things, we actually get 0.064, all right? And because they are equal, all right, they are independent. Okay. Right. On to our next question, question number 3. Suppose event A is 6 times more likely to happen than event B, all right? And they are mutually exclusive. Now, we've been told that probability of A or B is that. We've got a formula for probability of A or B. The probability of A or B is actually equal to the probability of A plus the probability of B minus the probability of A and B. Okay? But we know that these are mutually exclusive. If they're mutually exclusive, this is 0. Okay. We also know that event A is 6 times more likely to happen than event B. So instead of event A here, I'm actually going to write 6 times the probability of event B. And this comes to 0,84. That's what they told us there. Right? And now we've only got one variable in here, the probability of B. 7 lots of the probability of B is 0,84. Divide both sides by 7, and we get that the probability of B is 0,12. Okay. Right. I'm going to have a quick sip of water. And we're going to move to question number 4. Okay, nice question. I spin the spinner, all right? It's got 9 equally sized sectors, so each sector's got an equal chance of coming up. What's the probability that I don't get a red? All right. Now, you could work out the probability of getting a red. The probability of getting a red would be 2 out of 9. So the probability of not getting a red would be 1 minus 2 out of 9, or just 7 out of 9. Obviously, you could also calculate that by just saying, well, I'd be happy with blue, green, or yellow, and there's 7 blue, green, or yellow sectors. What's the probability that I get green or blue? All right. Okay. And this is just basically going to be, we're happy with green or blue. So we've got 1, 2, 3, 4, 5, 6. And that's going to be 6 out of 9. Notice that is actually the same as the probability of green plus the probability of blue minus the probability of both. And they're mutually exclusive. You can't get green and blue. Okay. Now, the probability of 2 greens and 2 spins. And this is where the 2 conceptual tricks in probability, the sort of like little tools that we can use. One is a Venn diagram and one is a tree diagram. And they're helpful in terms of us thinking about our thinking, right? I'm going to actually think of my 2 spins. And I'm going to draw a little bit of a tree diagram here. Okay, I could get a green, right? Or I could get a non-green on the first spin, right? And the probability of getting a green on the first spin, right, would be, sorry, I want 2 greens in a row. So actually, I'm going to use this for the next question, actually. But, all right, the probability of getting a green on the first spin would be 2 out of 9. And the probability of getting a green on the next spin, another 2 out of 9. Okay, and because they're independent, I can multiply. And so, in fact, the probability of getting a green on 2 greens and 2 spins, 4 out of 81. Okay. Right, now I'm going to look at the probability of getting 1 red in 2 spins. And I'm going to just, in fact, you know what, I'm going to I'll start again with my tree diagram. Okay, so on the first spin, I could get a red or a non-red. On the next spin, I could get a red or a non-red. Okay, and if I got a non-red on the first spin, I could again get a red or a non-red on the second spin. Okay, so we just remind ourselves of the probabilities. The probability of getting a red is 2 out of 9. Okay. Probability of this is 2 out of 9. Remember, whenever a tree diagram splits, the probabilities have to add to 1. So this must be 7 out of 9. And that makes sense because there are 7 non-reds, right? Maths always makes sense. Okay. If I was to spin again, and the probability of getting a red again now would be 2 out of 9. And a non-red, 7 out of 9. Here, 2 out of 9. And 7 out of 9. Now, I want 1 red in the 2 spins. So I don't actually want to operate on the top branch, which gives me 2 reds. And in fact, I don't want to operate on the bottom branch, which gives me no reds. I want to take this branch, and I want to take this branch. Okay, and now remember the probability at the end of a branch, the probability of this thing happening. We're going to multiply. We're going to get 14 out of 81. We're going to multiply those two fractions, 2 nines and 7 nines, 14 out of 81. This is also 14 out of 81. Just because we can, this is 49 out of 81. And the top is actually 4 out of 81. And if you add all of these together, behold, you get 81 out of 81. Right. Those are that's what we call exhaustive. Those are the only things that can happen, and that's why all the probabilities are included in those. Okay, they add to 1. Okay, but the probability of 1 in red and 2 red spins is on this branch or this branch, or we're going to add, so 28 out of 81. Okay, the probability of at least 1 blue in 5 spins. Now, we don't want to really be going and drawing a complicated tree diagram here, but what we know, and this was on the sort of formulae slide that I put up at the front, that the probability of at least 1 is 1 minus the probability of none. Okay, now the probability of none means I must get a non-blue, all right, and the probability of a non-blue is actually 5 out of 9, all right, but I want to get that on the first spin. I want to get a non-blue, and then another one on the second spin, and another one 5 times. Right. And so this will be the probability that I get 5 non-blues, right? And the complement of that is getting at least 1 blue. This comes to 94.7%, which is kind of what you would expect if you spin the thing 5 times, that you'd get at least 1 blue. That would include getting 5 blues, although getting 5 blues would be very unlikely. Okay, now this is an interesting one. The minimum number of times I must spin it to be at least 90% sure of getting at least 1 yellow. Now, there's only 1 yellow on the thing, right? So probability of at least 1 yellow is going to be 1 minus the probability of no yellows. So the probability of no yellow on the first spin is actually 8 out of 9. Right? Now, I want that to happen again on the second and on the third and on the fourth. I don't know how many spins, so I'm going to make that equal to n, and I'm going to make this equal to 0.9. Right, I want the answer to be 90%. Okay, this answer for at least 1 yellow. Now, nice little thing here, a log equation, or sorry, an exponential equation, the variables and the exponent. So we're going to use our log law, all right, and we're going to use logarithm function rather. So 8 ninths to the n is actually equal to 0.1. And then n will equal log, remember the base is always the base. There's the base, all right? And here's the base. 8 ninths of 0.1. And when we do that, we actually get 19.55. You can't spin it 19.55 times. If you spin it 19 times, you'll actually have a slightly less than 90% chance. And if you spin it 20, then you'll have a slightly more. But remember, we want you to be at least 90% sure. Okay, so we need to spin it 20 times. Okay, right. The next question is around the shading of some Venn diagrams. Okay, and we are looking now to shade not A and not B. Now remember, the important thing with the word and, both have to be true. If your mother says to you, you can go out with your friends after you've tidied your room and you have washed the dishes, you have to do both things, right? If your mother says you can go out with your friends after you've tidied your room or you've washed the dishes, you can go if you've done either, and you can certainly go if you've done both, right? But or is true if either is true, and is only true when both are true. Okay, here, not A and not B. So both things have to be true. this is certainly not A and not B. I have to make this highlight a little bit finer here. All right. And basically, it's going to be everywhere here. I can't go into either circle because as soon as I go into a circle, A will be true or B will be true depending on which circle I've gone into. So that's the shading for that one. Right, the next one says not A and B. That means I must be in the B circle. All right, I'm now on the next diagram. I must be in the B circle, but I must not be in the A circle. So I'm just talking about this little piece over here. So I became a maths teacher. Okay, there it is. Okay, the next one, A or B. And this is really, really important. Well, anywhere in the A circle or anywhere in the B circle. Okay, and this, we're going to come back to this because this diagram really helps us understand that formula that we get given. And then lastly, A or not B. Right, now A or not B, this is A, that's definitely true, all right? But not B, this is true for not B here, all right? Okay, and the only place, in fact, that I can't shade here is in here, because in here I've got B and not A, all right? And so neither of these two things would be true. So in fact, this particular one looks like this. Basically everywhere, all right, I've never been very good at staying inside the lines. Everywhere but that piece that is B and not A. Okay. Right. I've really tried to work quite hard at finding a sort of mix of questions. Okay, this question over here says, the probability that Pumlani finishes the comrades is 0.8. The probability that Sanele finishes is 0.7. And the probability that both finish the probability that either of them finishes is 0.94. Right, now we've got a formula for or. So the probability that Pumlani finishes or Sanele finishes, that's going to be the probability that Pumlani finishes plus the probability that Sanele finishes minus the probability that Pumlani and Sanele finish. Okay, now we are told that this is 0.94, 94%. This, the probability that Pumlani finishes is 0.8. And the probability that Sanele finishes is 0.7. Right. The only thing that I don't know now is the probability that they both finish. And I can solve for that. And if I solve for that, I get that the probability that they both finish 0.56. Now the question says to me, are their chances of finishing independent or not? Okay, and now I'm going to check this out because separately here, I'm going to work out what's the probability that Pumlani finishes multiplied by the probability that Sanele finishes. And this is actually 0.8 times 0.7. And 0.8 times 0.7 is 0.56. Because these things are the same, right, their chances of finishing are independent. Okay. Right. Onwards and upwards to question number 7. Okay, this question tells us the probability of not A and B is 0.6. So I'm going to call that one A and I'm going to call it tells us that the probability of not A and B is 0.6. This area here is not A and B. It tells us that the probability of A and B is 0.2. And it tells us that the probability of A is 0.3. Right, so 0.3 must be made up of everything that's inside A, which means that this must be 0.1. Right, which means that I've got 0.9 so far, which means that this must be 0.1 as well, coincidentally. Okay, then it says Are A and B mutually exclusive? No. All right? Because the probability of both is not 0. I know there's a bit of repetition here, and that's with intent. Okay. Are they independent? Well, now this, and recently I tested a class on this, and most of them got it wrong. Because when they worked out the probability of A times the probability of B, they didn't take the probability. This is not the probability of A, guys. 0,1 is not the probability of A. The probability of A is 0,3, and the probability of B is 0,8. So let's work out what is the probability of A times the probability of B. Right, that comes to 0,3. I'm just going to show you again. 0,3 is probability of A times 0,8 probability of B. And that comes to 0,24. All right. But we were told that the probability of A and B is 0,2. Sorry. The probability of A and B is 0,2. Therefore, not independent. All right. If they're not independent, then we can say that they are dependent. All right. But the question actually said, are they independent? So I'm just going to say no. Right. If they're not independent, they are actually dependent. Okay, now what's the probability of not A and not B? And now we just got to think, where is it true that A is not true and B is also not true? And that's this 0,1 outside here. And then lastly, the probability of A or B. Right. Now, remember the probability of A or B is actually the probability of A plus the probability of B minus the probability of A and B. And I'm just going to show you why this rule actually works and why it makes sense and why, in fact, all of maths makes sense. Right. If we want to know A or B, we want to be anywhere inside here. If we take the probability of A, all right, we're counting all of that. If we take the probability of B, we're counting, sorry, not perfectly drawn, we're counting all of this. Okay, and what are we doing? We are double counting the 0,2 in the side. And that's why you can see we're going to take the whole of the stuff in the left-hand circle, everything in the right-hand circle, and then we're going to subtract the intersection. We're going to subtract the intersection. Right, and that's why the formula is how it works. Okay, and really helpful to try and understand this maths rather than just learning it as a series of recipes and rules. Okay, the next question is about Taylor Swift. And I hope she doesn't need royalties for this. But so on my phone, I've got a playlist and it's got 9 songs, and it plays them, as you know. Playlists is, if you shuffle it, it'll play them in random order, and it won't replay a song until all the songs have played. 4 of them are by Taylor Swift. So we're going to draw a tree diagram, and we're going to use it to determine the probability that exactly 2 of the next 3 songs are by Taylor Swift. To save time, I've drawn the structure of the tree diagram here. This is the first song, second song, and third song. Okay, now I'm not worried about what other artists are involved. I'm actually just interested in, is it by Taylor or not by Taylor Swift? By Taylor or not by Taylor? 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 And while I'm just finishing this off, maybe you can think about, is each song independent or dependent of the previous song? Right? Is this an independent or a dependent arrangement? It's actually a dependent thing, because the song that plays here will influence the likelihood of what happens next. So the probability that the first song is by Taylor Swift, there are 4 of them, all right, out of 9, is going to be 4 out of 9. That means that this must be 5 out of 9, a non-Taylor Swift song. Now, if a Taylor Swift song is played, then that one won't play again. So now there's only 3 Taylor Swift songs out of 8 to play, which means that this must be 5 out of 8, which makes sense because the non-Taylor Swift songs haven't played yet, and so on and so forth. This will be 2 out of 7. Right, this must be 5 out of 7. Okay, here, one of each is played, right? So this, in fact, will be 3 out of 7 because there are 3 Taylor Swift songs left and there are 4 non-Taylor Swift songs left. This will be 4 out of 7. Likewise here, 2 Taylor Swift songs, so a Taylor Swift song's played and a non-Taylor Swift song. So there are 3 out of 7. This must be 4 out of 7. This bottom one, I'm actually going to go from the, so this has got to be, if a non-Taylor Swift song is played with a probability of 5 out of 9, the chance of another one of 4 out of 8. This must also be 4 out of 8 because every time a branch splits, it must add to 1. If 2 non-Taylor Swift songs have played, then there are 3 remaining out of the 7 songs, and then this must obviously be 4 out of 7. If I multiply down these branches, okay, all of these have the same denominator of 504. But the ones that I'm interested in are the ones where Taylor Swift occurs exactly twice. And I'm going to just highlight those branches, right? So here, Taylor Swift, and a non-Taylor Swift. Here, Taylor Swift, a non-Taylor Swift, and then another Taylor Swift. So 2 Taylor Swift songs. And then lastly, here, we start off with a non-Taylor Swift, but we then have 2 Taylor Swift songs. You'll notice that all of these fractions are actually the same, right? So I'm not going to work them all out. 4 times 3 times 5, 4 times 3 times 5, actually 60 out of 507. Okay, but that fraction there is repeated there and over there. So actually, the answer to the probability that 2 of the next 3 are by Taylor Swift will be 3 lots of 60 over 507. That's over 504 rather, 180 out of 504. Okay, and there it is. Okay, onwards and upwards to question 8. A bag contains 1 green bead and 3 red beads. John and Tandy take turns removing a bead. So they take it out from the bag. Tandy goes first. The person who draws the green bead wins. Now this question actually surprised me. I made it up. And I assumed that Tandy would actually have a greater chance of winning by virtue of going first. Right, let's just have a look at what happens here. Right, so the first draw is Tandy. And Tandy either gets a red bead or a green bead. Chances of a green, sorry, I'm not going to write those there. I'm actually going to write them here, red or green. The chances of a red, 3/4. The chances of a green, 1/4. Now, at that stage, the game is over if Tandy draws the green and he's won. Okay, so we don't need to carry on with that branch. Now it's John's turn. So I'm just going to change pen color. So I'm going to do all John's turns if I remember correctly. If I remember to, I'm going to do John's turns with a black pen. All right. John could get a red bead or a green bead. Now, there are only, Tandy removed a red bead, so there are now only 2 red beads left out of 3. So John's got a 2/3 chance of kind of not winning at this stage, and a 1/3 chance of winning at this stage. Okay, this here would represent a win for John. I'm just going to put a kind of a blue tick for John's wins. Okay, all right. If 2 reds have come out in a row, Tandy now gets another turn. So I'm going to use the red pen to show Tandy's. Now there's only 1 red left, okay, and there's 1 green left. So Tandy's now got a 50% chance of getting the red and a 50% chance of getting the green. Okay, and that would represent a win for Tandy. So there's 2 ways in which Tandy can win. Right. If the red bead came out now, it's now John's turn. And in fact, now there are no red beads left. So the probability of getting a red bead is 0. And there's only 1 bead left and it's green. And so this probability is 1. Okay, and that would represent a win for John. Okay, so now what we got to do is we got to add Tandy's chances of winning together. All right, and so Tandy could win right up on the first. So the probability that Tandy wins is going to be a quarter, and then plus the probability of getting to this next green tick. And remember, we multiply down the branches. 3/4 times 2/3 times a half. 3/4 times 2/3 times a half. And lo and behold, this actually is in this fraction here, I can divide there, I can divide there, and I actually get a quarter in the bracket. So I get a quarter plus a quarter. So in fact, it actually works out that Tandy's got a 50% chance of winning. And if you wanted to check, you could check the branches that John is down, obviously also 50. Right. So it actually doesn't matter who starts the game, which is interesting. Now, and this question came up actually in an exam a few years ago, a kind of a version of this question, all right? But the game now is a slight variation where the bead is replaced, right? Now the game theoretically never ends, okay? And there's a cool sort of tie-in to what we were looking at yesterday, all right? Which was sequences and series. Okay, so this is Tandy's turn. And Tandy could get a red or a green. Chances of a green, a quarter. Okay. The chances of a red, obviously 3/4. Now it's John's turn. I'm going to use the black pen as I did previously for John's turn. John could get a red or a green. If John gets the green, it's game over. All right. So this here represents a win for Tandy. If John gets a green here, and the chances of that are, notice now, because the bead's been put back in, the probabilities are now fixed at 3/4 and a quarter. This would represent a win for John. Okay, we're actually interested in the probability of Tandy winning, so let's just carry on down here. Here, Tandy would win with a green, all right, and the chances of that would be a quarter. And 3/4 would be a red, and the game would go on. Okay. Now, if the game goes on, then it's John's turn, and John could get a red with a 3/4 chance, or a green with a 1/4 chance. Okay. And at this point, John would win. Okay. Now, what we can see, right, is that if we just look at Tandy's chances of winning, okay, probability that Tandy wins. Tandy could win here on the very first turn, or down this branch over here. Okay, and this branch is actually going to be a 3/4 times the 3/4 in order for John to also get a red, times a 1/4. So this is going to be a quarter. This is going to be a quarter times 3/4 squared. Now, for Tandy to get another turn, we need the 3/4 to happen. So I'm just checking this. This probability of Tandy winning is actually 3/4 times 3/4 times a quarter. All right, which is correct. The next one would be the way Tandy would win next would be 3/4 times 3/4 times 3/4 times 3/4, and then times a quarter. All right. So the next one would be actually a quarter times 3/4 squared. Right. And this is actually an infinite geometric series. A is a quarter, and R is 3/4 squared. And the sum to infinity, right, is obviously going to be a quarter. Like, I'm starting to just be slightly concerned because I'm getting a slightly different answer to what I got on my memo earlier. But I think it's, and I'll check the memo and I'll make sure the memo that's published is correct. But I'm pretty sure A is a quarter. Yeah. So A is a quarter. So in fact, the probability is going to be a quarter, that's A, over 1 minus 3/4 squared. Okay, and in fact, I think this answer is correct because I think it's going to come out to slightly more than 50%. It's just okay. We will use it. Right. So it's going to be a quarter, 0.25, 0.25 over 1 minus 0.25 squared. Okay. And sorry, not 1, 1 minus 0.75 squared. All right. And we get 4/7 as the answer. And I'm quietly confident about that. This time, Tundi benefits from starting. Okay. Right. Onwards and upwards. We're now onto the counting technique stuff, and we sort of making good progress here. So a computer code takes the following form. It has 3 digits which may not be repeated, followed by 2 letters which may be repeated. So here's an example. So there's three letters which are not repeated, and then there are 2 digits. 3 digits and then 2 letters. It says how many such codes are possible. What I like to do is I like to write out the sort of format of the code. There's the 3 digits and then 2 letters. And on here, I'm not writing the letter, but I'm writing the number of choices. The number of choices for this first digit is actually 10, because I could have everything from 0 through 9. Now, I'm not allowed to repeat. So for the next digit, I've only allowed a choice of 9. And remember, the fundamental counting principle says we multiply our choices. And for the next digit, only a choice of 2. Now I'm choosing the letters, and I can choose any letter. So I've got a choice of 26, and letters may be repeated. So in fact, I've got a choice of 26 again. This all multiplies out to 486. Sorry, 486, 720. Okay, now suppose that we're going to keep the format the same. We're just going to add some extra letters in. And we're going to add some extra letters in order to be able to build 20 billion unique codes. Okay, and what's the fewest number of letters that we need to add? Okay, so, and it does say calculate. So we're not going to get an answer just by sort of guessing and checking on a calculator, right? Again, our number of codes is actually going to be 10 times 9 times 8, and those are for the digits at the front. And then we're going to have 26 times 26 times 26. Suppose we have n letters altogether, right? We need this to be at least as big as 20 billion. Okay. We're going to solve this. And what do you think we're going to use to solve this? Indeed, we're going to use log. We're going to firstly divide both sides by 10 times 9 times 8. So 26 to the n is actually going to be 20 billion. Over 10 times 9 times 8. And now I want to get that exponent on its own, and I'm going to use log. And so in fact, n is going to be log, and the base is always the base of this stuff. 20 billion over 10 times 9 times 8. And I get 5,3. Right, now I can't have 5,3 letters, so I actually need 6 letters. But here's a little exam technique. Before you finish, just read the question again. All right, it says the minimum number of extra letters which will be needed. Okay, I had 2, I need to go up to 6. So 4 extras will need to be added to give me the requisite number of codes. Okay. Right, Adam is forming 5-digit numbers by choosing from the digits 2, 3, 4, 6, 7, 8, and 9. All right, how many numbers can Adam form? Again, I'm going to write some little lines here, and on those lines, I'm going to write a number that's not the digit, but in fact the number of choices for the digit. Now, there's only one of each of the digits, so he can't repeat a digit. So he's got a choice of 1, 2, 3, 4, 5, 6, 7 for the first choice. Now he's used one of them, so he's only got a choice of 6, and then a choice of 5, and then a choice of 4, and then a choice of 3. And that's our answer. Right, that answer actually comes to 2,520. Okay, and now for the first time, counting techniques is going to intersect with probability, which it often does. Right, one of the numbers that he could possibly make is chosen at random. What's the probability that it's even and it exceeds 70,000? Okay, now this requires a bit of thought. This is actually, there's some nice thinking involved here. Right, firstly, if it's even, right, and I'm just thinking about these kind of numbers here that we can remember, it's a 5-digit number that we're going to make. Right, we could put in here a 2. So it's got to end in 2. Right, and now we're going to work out what other digits we could choose. Okay, so this 2 actually doesn't represent choices, it represents that there's a 2 there. With the green pen, I'm going to write choices. Okay, now this number has to start with 7, 8, or 9 in order to exceed 70,000. Right, so that's important. So there's actually only a choice of 3. And now if you think about it, I've used one of those numbers, and I've also used the 2. So I've actually now only got a choice of 5, and then a choice of 4, and then a choice of 3. All right. For my digits. Okay. And so over here I get 20 times 9, I get 180. There are 180 even numbers. So not even numbers, 180 numbers that end in 2, all right, that exceed 70,000. Okay. Now, we're looking for 5-digit numbers, 1, 2, 3. They are 5-digit numbers, yes. Right. Now, the other possibility, obviously, is that the thing could end in 6. All right. And if it ends in 6, actually, sorry, if it ends in 4 or 6, exactly the same thing is going to happen. Each of these is going to end up with 180 possibilities, right? Because I could still only have a choice of 3 for the front here. Okay, now the last possibility is that it ends in 8. And if it ends in 8, so remember this black 8 is not a number of choices. It's saying we're using 8 at the front there, sorry, at the back there to get the even number. Now, these 4 digits, I no longer have a choice of 3 because I can't use 8 because I've already used 8. So I've only got a choice now of 7 or 9. All right, to be bigger, 7 or 9. And then, so that's a choice now, and I use my green pen for choices, a choice of 2, right? And then a choice of 5. It will be 5 still because I've used the 8 and I've used one other, so it'll be 5 times 4 times 3. And so this time I get 20 times 6, I actually get 60, right? Just checking that. 20 times 3 is 60, times 2 is 120. 120. Okay, if we add all of these up, 3 lots of 180 is 540 plus 120, 660. There are 660 even numbers that are greater than 70,000. Now, we have not finished the question because the question talks about a probability. And lo and behold, that formula that I keep saying is a little bit unnecessary, but we end up using it all the time. The probability of getting such a number is the number of them that exist over the total number of things that can happen. So our final answer, the probability of being even and bigger than 70,000 is going to be this number of, so it's not 666, it's 660, all right? 660 divided by the sample space, which I worked out in A, the total 2520. Okay, I haven't got it as a percentage, but I don't think it really matters. Okay, we're nearly there. Question number 12. Fundi arranges her 8 books randomly on the shelf. What's the probability that the 3 maths books are all next to one another? Okay, so what's the total number of arrangements? The total arrangements is just going to be 8 factorial. No restrictions. Okay, now what's the total if the maths books are together? And remember the conceptual trick that we're going to use here? We're going to use a rubber band. Okay, so I'm going to just draw a little bit of a picture of what we've got here. Remember, we've actually got a total of 8 books. So we've got book 1, we've got book 2, we've got book 3. They're all different. We've got book 4, we've got book 5, and then we've got 3 maths books, okay, which are also all different from one another, but they have something in common. They are maths books, right? M1, M2, and M3. So what we're going to do, we're going to get a rubber band. It happens to be a green rubber band, and we're going to put it around these books. And now if we count how many books we've got, 1, 2, 3, 4, 5, 6 books. And 6 books can actually be arranged in 6 factorial ways. But for any one of those arrangements, those 3 maths books can themselves move into 3 factorial arrangements. So we need to multiply by that. So that's the total number of ways for the maths books together. So the probability that the maths books are together is going to, again, we're using that little formula. It's the number of ways that it can happen, which is 6 factorial over 3, sorry, 6 factorial times 3 factorial, divided by the total sample space, which is 8 factorial, and we get a final answer of 10.71%. Okay, right. Onwards and upwards to question number 13. Consider these letters, the letters of the word mathematical. How many different words can be formed using all the letters? Well, what we've got here, we've got a total of 11 letters. So 11 factorial, if they were all different. But there are 2 T's, there are 2 M's, and there are 3 A's. And so we need to divide out for that. We end up here with, it's actually a lot, it's 1.6 million, 1,663,200. Okay, that's how many different sort of words are possible. They're not going to all make sense. In fact, most of them won't make sense. All right. Now, if we choose one at random, what's the probability that it does not start and end with the same letter? The way I'm going to tackle this, I'm actually going to work out how many can we make where they do start with the same letter. All right. So do start, struggling with my pen width here. Do start and end. Yeah, and this is obviously they can't start and end with I because there's only one I. So we've now got to consider different cases. If they start and end with M, right, then those M's are out of the equation and we've got 9 letters left. And 9 letters can be arranged in 9 factorial ways, but we've got to divide by 2 factorial because there are still 2 T's and 3 factorial because there's still 2, as there are 3 A's. If it starts and ends with T, exactly the same thing. 9 factorial divided by 2 factorial for the M's and 3 factorial for the A's. But and I'm just going to change pen color here. If it starts and ends with A, you'll notice it's actually slightly different because now it's 9 factorial over 2 factorial times 2 factorial. Okay, and we can add all these numbers up, all right? And we can get the total, we add them all up, total, and then we're going to divide by our sample space, which was 166. Sorry, this is a total where they do start and end, start and end with the same, all right? And we divide by that answer that we got of 63200. Okay, so that will give us the probability that they do start and end with the same letter, and the probability they don't, and this actually comes out to 1 in 11. All right, so the probability, and this is the idea of the complement, that they don't start and end with the same letter is going to be 1 minus an 11th, or just 10 11ths. Okay, right. We have got, I think, one more question to go after this one. Right. So Alexandra, who I think might have been watching some of these has cards with the following digits on. She's got just one of each card, and she's forming numbers using some or all of the cards. So she could make a number like 21, where she uses just 2 cards, or she could make this number or this number. How many different numbers can she form in this way? Well, here we've got to think about the sizes of the numbers. All right. How many 1-digit numbers could she make? Well, she could only make 5. There'll be 5 of those. How many 2 digits? If she wants to make 2-digit numbers, how many choices has she got for the first digit? 5. And for the second digit? 4. She can make 20 2-digit numbers. 5 1-digit numbers. If she wants to make 3-digit numbers, then she's got a choice of 5 for the first digit, then 4, and then 3. And that happens to come to 60. So there's 60 3-digit numbers she can make. If she wants to make 4-digit numbers, she's got a choice of 5, a choice of 4, choice of 3, and a choice of 2. And just what we're going to get here is we're going to get 120. All right? And in fact, if she wants to make, so these are 4-digit. If she wants to make 5-digit numbers, and I'm sorry, I'm going all over the show here, 5-digit, she's got a choice of 5, she's got a choice of 4, she's got a choice of 3, she's got a choice of 2, and in fact, there's no choice, there's just one that she's going to use for the last one. This is also 120. So we add all of those up. 240, 325. Final answer, 325. Please, in an exam, set your work out better than I'm setting it out right here. I just didn't leave myself enough space for this question. Okay, then, what's the probability that the number she forms is bigger than 5,000? Right. Now, 5,000's only got 4 digits. All of her 5-digit numbers will be okay. All the 5 digits. 120 of those. All right. But what we now want to work out is how many of the 4 digits would be okay. Right. So if it's a 4-digit, in order to exceed 5,000, all right, it must start with 6 or 8. Right, so we've only got 2 choices for our start digit. Then we've got 4 choices for the next digit, and then 3 choices for the next digit, and then 2 choices for the next digit. And this comes to 8, 24, 48. Right. Eight, 24, 48. Yeah. Right. And so, in fact, there are 168 numbers that she can form that are bigger than 5,000. So the probability of being bigger than 5,000 is going to be 168 out of our 325. Right, comes to about 51.7%. Okay, and our last question, or second last question perhaps. A group of 6 friends goes to the movie. Johan hopes he won't be sitting next to Peter as they recently had a disagreement. What's the probability that they're not seated next to each other? Right, so we've got person number 1, we've got kind of person 1, person 2, person 3, and then we've got Johan and we've got Peter. And the way we're going to work out the number of ways that they don't sit next to each other is by means of a complement. We're going to work out if they did sit next to each other. All right. So, firstly, just the total number of arrangements that you can seat 5 people is 5 factorial. 5, all right, 120 arrangements. Now, if Johan and Peter are next to one another, all right, then we put a rubber band around them. There's 4 people, all right, so this is J and P together next to each other. Now we've got, effectively, we've got 4 people who can be arranged in 4 factorial, but we need to multiply by 2 factorial for the fact that they can swap around inside the rubber band. Okay, so we get 4 factorial is 24 times 2, we get 48. Right. So there are 48 arrangements where they are next to one another. So that must mean that there are 72, 120 minus 48, 72 not sitting together. All right, and let's just check what the question asks. It actually asks for a probability. So what's the probability that they're not together? All right, probability that J and P are not together, not next to each other, is going to be 72 out of the total, 72 out of 120, right? And that comes to 2/3, 66.7%. Okay, and now we are on to our very last question. And I know some of you might be surprised because I didn't include this initially. I have updated the questions that are online, so I'm hoping now, if you're watching the video, you'll be watching the latest version. This is what's called a two-way contingency table, and I just thought I didn't want to leave it out. Right? First thing is to complete the table, and that's fairly obvious because if we can work out the totals here, so I'm not going to spend any time on that. Right, that's 852, that's 95, and then this here is 232. 232. And this asks us to determine whether hot drink preference is dependent of left or right-handedness. Okay, and we need to justify our answer with a calculation. What we're going to do, we're going to take one specific possibility, being left-handed, for example, and liking tea. Right. And the probability of finding such a person, well, there are 19 left-handers who like tea out of our total sample space of 1160. And if we work that out to a kind of a decimal, it's 0.01637. Right? And now what I'm going to do separately, remember that test of independence, I'm going to work out the probability of being left-handed from this sample and multiplied by the probability that I get someone who likes tea from this sample, right? And so the probability of a left-hander, well, there are 95 of those people, so 95 out of 1160, and I'm going to multiply that by the probability that I get someone who likes tea, and there are a total of 232 people who like tea, and I multiply these two things together, and in this particular case, I get 0.01637. I get exactly the same number. And because these are equal, these things are independent. All right. So it's not dependent. In other words, what it's independent. What that means is it makes no difference whether you're left-handed or right-handed as to whether you're going to prefer tea or coffee, which is probably what one maybe might expect. But remember that you're not guided by your opinion on this. You're guided by the data and by the numbers. Okay, folks, that was a long session. I found it long, and I'm quite sure you did as well. All right, and I know some of this might have been a little bit heavy going, but remember the obvious advantage with the video is that you can pause it. Right. Remember that the solutions will be up shortly, and yeah, please. I know I keep saying banging the same drum, but if you're finding these useful, please share, like, and subscribe. If you want to contact me, I will. I'm just going to put my email address up, right? Which I actually wanted to make a better looking slide of that, but it's just Paul at Shire. Sorry. Right, so if you've got any kind of queries or questions, you're welcome to email me. All right. Thanks very much. Have a wonderful day. Bye now.